Hey everybody, and welcome to ABB's top 5 common pH measurement headaches and how to overcome them. Just before we get started, I'd like to introduce myself. My name is Robert Mapleston. I am the Marketing Communication Manager for the Continuous Water Analyzer line at ABB. And I'm sorry about that. And just some housekeeping details. There is a Q&A function, as you can see on your screen. So we'll be having a Q&A session at the end of this webinar. Feel free to post any questions you like during the webinar. You can type that in the Q&A using the Q&A function. And as I said, we will get back to you at the end there and go through the questions that you post. Also, any technical issues like I'm just having, please use the chat function for that. And we do have a moderator in the background that'll help if you have any technical issues. And most importantly, too, from a safety point of view, we do want to keep you safe. So we can move on to the next slide, please. Just a quick safety moment. Obviously, you know, a webinar, we want you to be engaged and listen and watch the presenters, but please do it safely. If you're walking around or if you're driving especially, please stop, pull over. This is being recorded, so we will be sending you a recording of this. So if it's unsafe for you to listen and watch this webinar, please stop and we will send it to you. But if you're in a safe place and you're listening, that's great. And we're happy you're joining us today. So again, thanks for joining the webinar today. I'd like to introduce our speakers. First of all, Nick Shevek, who is the Global Product Manager Analysis with Measurement Analytics. He will be doing most of the presentation today, and then a bit later on, the go-to guys for help with the pH technology at ABB will be joined by Jimmy Dennis, who is a technical sales specialist for continuous water analysis in the US, and also Gus Gregorek, who's also a technical sales specialist for continuous water analysis in the US. So Jimmy and Gus will join a bit later, but to begin with, we'll hand it over to Nick. So over to you, Nick.
Great, thank you, Rob. So hello, everyone. Thanks for joining today's web presentation. As the title suggests, we're going to go over some common issues or headaches that you commonly find with pH measurement. pH measurement is one of the more common parameters that you find in industrial applications, especially where water is involved. So we want to make things really simple and easy for you guys to not only select the right product for the right application. If you look in the market currently, there's a lot of different options in terms of sensor styles, configurations, hardware options. And depending on the selection you make, could make a difference between a probe that lasts maybe a day in the process to something that lasts maybe a few more months. So it definitely pays off having the right selection for the product, or for the application, I should say. Then we'll go over some common maintenance issues when dealing with pH. Although pH is a very simple parameter, there are a few things you need to keep in mind when it comes to cleaning, calibration practices, and also location considerations. That will help definitely make a difference in terms of accuracy, performance, and longevity. And then last but not least, some common troubleshooting techniques, mainly around verifying samples. Usually this comes up often where customers will take a lab reading or a benchtop or a handheld reading, and the results from that can wildly differ from the process reading they have in your pH sensor in the process. So kind of tips and tricks on how to align those two together and make sure that you get consistent results. So before we start, we want to kind of gauge some of the audience members in terms of involvement in pH and their understanding. So we'll take about 20-30 seconds to go through this poll, and I believe Rob will pull this poll up, so you should see something pop up now. So again, we'll take 20 seconds real quick just to answer that poll, and then from there we'll look at the results and continue on. All right, so based on those results, Rob, do you have the... There we go, perfect. So I'm looking at the results now. It looks like a majority are interested purely in general understanding of application. So we'll kind of go through that portion as well. If there are any questions, as Rob mentioned, there is a question icon in your meeting. Definitely submit your questions, and we'll have a 15-minute section at the very end to go through some of the questions that you might have. All right. So let's continue on. There we go. Sorry. So pH monitoring, why it's important. pH monitoring, as I mentioned, is a very common parameter, whether it's industrial, municipal applications. After flow, pressure, and temperature, it's the fourth most common measurement. And if you look at analytical specifically, it takes about 30% of all analytical measurement is tied to pH. So it's a very common platform and utilized in a number of different ways in various industries, whether it's regulatory in terms of emission or discharge for effluents in plants, making sure that the level of pH is sufficient to discharge and safe for the environment. It could also play a role in quality inspection for process-related control, chemical dosing and injection processes. So it's used widely in a number of different applications. But at the center, we're all dealing with a very common pH design, which shares a lot of headaches and issues from one application to another. So it's all dealing with very similar issues. So in this presentation, we'll kind of go through some of the common ones that we see from our experience. So speaking of issues and things customers deal with, we like to say pH is a permanent headache for our customers. And it's true. Although it's a simple parameter, it does present a number of different issues for our customers. The main one, the first one is basically, when you go to look at the market in terms of options for pH electrodes, you'll notice there's a number of different options, whether it's pH class options, pH class shapes, formulation variations that can make an impact in your application. Do I have the right product for the right application? Some customers pick the most durable sensor because they know it's very resistant to high temperature, but it might not work that well in high purity applications or low temperature applications. So selecting the right product for the application can make a difference in terms of your maintenance requirements and also performance of the product in the process. So in this presentation, we'll go over some quick guides and check, make sure you select the right sensor, the right glass option, the right reference design for your application. Then we'll dive into some maintenance headaches. Again, pH sensors are unlike temperature and pressure transmitters and sensors. They need constant attention and maintenance. So kind of giving you an idea of what common things contribute to drift in the sensor and how you can alleviate those, whether it's through proper cleaning techniques, solutions to use for cleaning, or mounting considerations that help extend the life of the sensor. And then last but not least, we'll go through sample analysis. So as I mentioned before, a big trouble or a big headache for customers when it comes to pH measurement is my pH sensor in process is reading 7 pH, but the lab results is reading 6.5. Why is that? So we'll go over some kind of reasonings behind why you can see deviation from your process reading into your lab result, and how to bridge the gap between the two so you get more consistent results. So first section is product selection. So again, I've kind of mentioned this before. In the market, there are a number of different options when it comes to glass selection, when it comes to reference electrode design and hardware, depending on if you're doing bypass sensor or hot tap retractable sensor. So it can be very confusing selecting the right sensor for your application. As I mentioned, most customers go for the most premium version when it's not really necessary most of the time. They can go for a more mid-tier or low-tier option depending on their application and get just the same performance at a lower cost. So at ABB, when we did our market surveys and asked customers of what is the most challenging part or one of the more challenging parts of their pH operation and maintenance side of things, the selection process was a clear indicator of, this is a challenging area for us. So we tried to introduce products that are very easy to select. They clearly define the application, what they're used for, what their benefits are, and what their downsides are to make the selection process really easy and save you time and effort in the process. So you can see here, there's an image exactly of kind of showing you all the different options and glass types that are typically available in the market. They vary in formulations. You have low temperature virgin glass. You can have high temperature virgin glass. Some are HF resistant or strong acid resistant type formulations. Some are sodium air formulations for those applications, for low pH applications. They come in different shapes. There are hemispherical type glass, bullet style glass, conical shapes. So they all come in different shapes and sizes, and it can be very difficult to navigate the process of making sure I select the right glass. So if we take a look at some of the common glasses that are available in the market, you'll notice that it kind of breaks down to 5 common platforms. And again, I'm not covering everything that is available because there's quite a bit, but these are the most 5 common. We'll cover probably 89% of the applications you run into. So the most first one you probably run across is general purpose type glass. This is basically a jack of all trades. It works over the widest range of pH. It has very good results kind of from top to bottom, but there are some limitations, especially when we start going to very cold temperatures or very high temperatures. The response to this might not be as great at the very low end, and it might not last as long at the very high temperature end. But in between, it's a good go-to sensor that works really well in most applications. Then we step into the high temperature virgin glass. So this one is designed as indicated in the title, high temperature applications. So typically above 50 degrees C or 122 degrees Fahrenheit. So this one works longer in high temperature applications. It'll have definitely a much longer lifespan compared to the general purpose glass, but where its weaknesses lie are low temperature applications. It won't be as responsive in those environments compared to an equivalent general purpose type glass. It'll be more sluggish responding, and you will see definitely deviation in your results if you compare one to the other. The next option is low temperature glass. So low temperature glass, as intended, is great for applications below 10 degrees C or 50 degrees Fahrenheit. And again, this works really responsively at the low end. So if you have effluent discharge, especially if you're up north, where in the wintertime seasons, you might get cooler temperatures. This will be ideal for those environments where you get more faster responding performance from your sensor. But where it wouldn't really work is high temperature applications, because it wouldn't last long compared to either a general purpose type glass or a high temp glass. So if you're looking for responsiveness at the low end, the low temp glass will be the go-to option there. Another very common option in pH electrode styles is the flat glass option. So the ones I talked about previously were mainly the hemispherical or bullet style glass, so dome shaped essentially. But we do also offer, and most competitors offer, flat glass options. So the benefit of a flat glass is that it's great for fouling prone applications or abrasive applications. Just glass, as we know, is very delicate and fragile. And same is true for pH electrodes. If you expose the sensor to high particulates, shock, damage like that, it will crack the glass and render the sensor inoperable. So the flat glass option is great for those applications where you can experience damage to the cell. But keeping in mind, you want to basically install a sensor perpendicular to flow. You don't want the sensor being exposed, or the glass being exposed directly to the flow conditions. So it's great for that environment, but it might not work well in low temperature applications due to its shape and geometry and its internal resistance. It'll be slow responding in low temperatures. And last but not least, you have HF resistant glass. And this is formulated specifically for hydrofluoric applications. Hydrofluoric acid actually will etch glass and eat glass over time. Unfortunately, there's nothing we could do really for it aside from making it much thicker and more robust. So the HF glass is great for HF resistant or HF prone or HF type applications, I should say. Now, the pH electrode is one portion of the pH sensor. The other portion is the reference electrode. So where the pH glass measures changes in millivolts based on changes of pH of the sample, which we want to measure, the reference electrode is the opposite end of the pH sensor in terms of measurement. So the reference electrode, the point of that is basically to provide a stable point of contact for the sensor. And it's typically surrounded by a salt solution of potassium chloride, KCl. And we want to protect that reference wire inside the reference electrode from any attack from the process, but also keep continuity from that wire all the way into the process, because it needs continuity between the reference electrode and the pH glass electrode to complete that circuit. So you'll find in the market a lot of different variations in terms of shape, size, structure, but they'll all consist of some kind of enclosure that has a porous junction at the end to keep the KCl salt in, and some kind of media that holds the salt inside as well. It could be a slurry, it could be a gel, it can be a wood or a solid matrix as well. But the idea is that it keeps the reference electrode protected, but also allowing for continuity between the reference electrode and the process. So the two main ones you'll find is a sealed design or a reservoir fed design. So the sealed design is great for industrial applications because, as the name implies, the reference electrode is sealed. There's no refurbishment or replacement of the KCl internally within the sensor. And it's great for high pressure, high temperature applications, especially industrial type applications. Where it wouldn't be really ideal is low conductivity or high purity applications, where there's a really massive draw of KCl salt out of the sensor. So if I were to use a seal design in high purity applications, that KCl salt would drain very quickly and you'd lose your continuity within the sensor. So on the other side of the spectrum, you have refillable or reservoir fed designs for the reference electrode, and they ensure that you have plenty of KCl salt feeding into the electrode body to make sure that the sensor works for prolonged periods and there's no issue of KCl depletion over time. Now, the downside to this platform, for the most part, is they cannot be pressurized, mainly because it's an open cell design. So any pressure you put in there will eject the KCl salt out. There are manufacturers who design bellows in their design to keep the KCl salt in, but for the most part, refillable electrodes or reservoir fed are not designed typically for high pressure, high temperature industrial applications because they will fail with time more readily than a seal design. So at ABB, as I mentioned, we did a lot of surveys with our customers to find out what some of the challenges are, and we did introduce a product line that makes it very easy to select and guide you in the right process of selecting the right product for the right application. So we structured our products in a color-coded fashion, each within their family. So we have a 100 series family, a 500 series family, and a 700 series family. The 100 series being just general purpose type applications, mainly for OEM, municipal, drinking water, wastewater applications. The 500 series is more for light to heavy industrial applications. And the 700 series is more specialty type applications, such as marine and high purity. So as you can see in the chart there, we have a number of different suggested target markets with their applications. And you can clearly see that for those target applications, we have a clear solution of what to pick depending on your requirements for that application. So at the end of the presentation, there is a link for additional information. So if you are interested in finding out more, feel free to use that link to find out more about pH measurement with ABB. So on to the maintenance tasks of the presentation. So as I mentioned, maintenance is a very critical aspect of maintaining accuracy and longevity of a pH sensor in the process. And a lot of times customers do struggle with this section. So a real life scenario we get normally asked is, my sensor needs constant maintenance and cleaning. I clean it every day and it still drifts really quickly after a day or two. What can I do to extend operation? And it typically boils down to a number of things. But if we look at what causes drift in the sensor, we'll find that there's two main areas we can focus on. One is drift caused by the pH glass electrode, and the other is the reference electrode. So what causes drift in the pH electrode typically is things like exposure to strong caustics, especially at higher temperatures. Think of the glass electrode as a lattice or a matrix of silicon dioxide or glass. And embedded within it are positive ions like lithium, potassium, essentially, that are responsive to changes in pH. Over time, things like strong caustics will deplete those ions in the glass matrix and make the sensor non-responsive. So unfortunately, there's not much you can do to extend the life of a pH glass electrode in those applications. Just make sure you have the right glass type selected. Typically, it's a high temperature version glass. If you could lower the temperature of the caustic or put it in another position where the temperatures are lower, it should help significantly extend the life of the pH probe. Things like high temperature also, again, as a standalone, will degrade the responsiveness over time. That's just naturally how it works. Again, picking the right glass type, the high temperature would work well in that environment. But things like abrasion and fouling, I've seen cases where, even with notched guards on the sensor to protect the glass, glass still gets etched and abraded, created by eddies in the process around the glass. So a flat glass might be a more preferred option because it minimizes the profile of the glass, and the flow will go basically directly across the glass without actually impacting it and making it less responsive with time. Drying out could also impact the responsiveness of the glass, especially if it forms a film on the outside. So ensure that where you mount the sensor is in an area where it doesn't dry off periodically. It stays wetted the whole time. Greasy deposits, any kind of general fouling will also, again, make the sensor unresponsive with time or drift with time. HF acid we talked about as well also etches the glass, makes it unresponsive. And then overall, just age of the glass. pH electrodes aren't made to work indefinitely. Over time, they will degrade and become less responsive. And this is true for even benign applications like drinking water. Over time, they'll start slowly becoming less responsive with time. And even acid etches, things like that, won't bring them back. So that's just the nature of the beast when it comes to pH electrodes. Now, on the flip side, the reference electrode, it has its own constraints when it comes to drift or what causes drift in the design. So the three main areas, and we'll cover this more in detail, are what's considered pumping, when you lose KCl salt, and that's typically in high purity applications. You'll have poisoning effects, which typically happen in more heavy industrial applications. We have strong chemicals present, where they'll attack the reference electrode that's within the reference electrode chamber. And then you have plugging, which typically happens where either a coating on the sensor happens on the liquid junction, or something embeds itself in the liquid junction, and the sensor loses continuity between the reference electrode located within the sensor to the process, and you get basically either non-responsive state or a very erratic response from the sensor. So again, we'll cover that in more detail in the next couple slides. So the biggest contributor to sensor drift when it comes to pH glass is the fouling and scaling effect. So this is the most common contributor to non-responsiveness. A lot of times you'll actually see the fouling effects on the glass sensor. It makes it easy to identify, but some cases you might not actually see it. So in one instance, we had a customer who was treating well water for contaminants, but the well water was very high in iron content. And if you look at the glass, it looked very clean. There was not much on it, aside from obviously looking a bit rusty. Hydrochloric acid did not work in bringing the sensor back. It was basically unresponsive. And it wasn't until an HF-based acid for cleaning specifically was used that actually brought the sensor back. So depending on the right solution or what you use can make a world of difference in bringing back the sensor back from the dead, essentially. But also more importantly is how you mount the sensor. So a lot of times customers will think, oh, if I mount the sensor directly inline or facing the process, the flow will actually help clean the glass, when actually makes the acceleration of fouling much worse. What you want to do always with pH sensors is mount them perpendicular to the flow, so the flow goes across the sensor and actually helps self-clean. And in really heavy prone applications where the fouling is really problematic, I'd always recommend a flat glass option just to minimize that profile and help clean, but also minimize the fouling effects on that glass electrode. And then worst case scenario, if you are prone to really high solids and high buildup, auto clean options are always a great way to minimize the time you actually go into these sensors. They'll help automatically clean the sensor periodically throughout the day for you. So when it comes to the reference side, we mentioned the 3 Ps, the pumping, poisoning, and plugging. So poisoning is probably the more common one in industrial applications where you have strong chemicals. So things that typically have either sulfides, ammonia, cyanide-based or bromide-based compounds, they are usually the most aggressive when it comes to attack of the reference electrode. So as I mentioned before, the reference electrode is protected by KCl salt in a sort of media. It can be gel, slurry, or a solid matrix. As long as the reference electrode is surrounded by KCl salt, it typically likes that environment. It's very stable and allows the pH electrode to measure the pH changes effectively. As soon as you start introducing other chemicals near or on the reference electrode, chemical reactions can start taking place. And that's very true for the ones I mentioned earlier, the sulfides, the ammonias. They'll start actually attacking the reference electrode, and you'll generate a millivolt value on the reference electrode where you really want a stable millivolt environment. You don't want erratic behavior on that one, because at the end of the day, the transmitter can't differentiate millivolt changes between the reference electrode and the pH electrode. So it'll be confused, and you'll start seeing swings in your valley or in your value on your transmitter when it's really chemical attack on your reference electrode, not changes in your pH. So how we protect that element, it makes a deal of difference. There are different junction types. There are Teflon versions, there are wood design versions, ceramic versions. So making sure you pick the right junction and the right reference design can make a world of difference. And from what we found in heavy industrial applications, a solid state wood design is the ideal preferred method for anti-poisoning effects, because it does slow down the migration of those elements to the reference electrode and helps extend life compared to either a slurry or a gel-based design for reference electrode. Now, on the opposite end of the scale, if you're looking at high purity applications, it has its own challenges, mainly pumping. So you start losing KCl salt very quickly. So having a reservoir-fed electrode design we talked about earlier could help extend the life of that sensor. And then last but not least, plugging. So things like oils that are non-conductive, scaling from minerals and iron-based kind of deposits will all essentially block the responsiveness of the sensor, because it plugs that porosity of that junction. So depending on if you pick a Teflon or wood design, each can combat better in either organic or non-conductive elements versus scaling kind of environments, depending on the selection. So what happens in pH poisoning effects is essentially, inside the sensor you have KCl salt solution. So over time that gets replaced with process. So kind of highlighted there is an illustration showing you basically process migrating into the sensor over time. And with time, it starts migrating closer and closer to the back of the sensor where the reference electrode is basically located. Now, as that boundary moves up and closer to the reference electrode, the sensor still works well, but what you'll see is an offset in your measurement. So at day 1 or week 1, you might see a 7 pH. At week 3, you might see 7.1, and then increase to 7.2, 7.3. Some of that drift can be attributed to this boundary layer being migrating closer and closer to the reference electrode. So it is very important to do a calibration periodically to offset those changes in the sensor. And that's just the nature of the beast when it comes to pH measurement. Location is also very important. Where you mount the sensor is going to make a difference in terms of how long it performs. So you want to avoid areas where they're close to a pump, near bends, restrictions. Essentially, you want to have as close to laminar flow as possible. Obviously, in this picture kind of shows you kind of the challenges customers might face. Laminar flow might not be possible in most environments, but you want to get to the point where it's as close as possible to laminar flow, because you don't want turbulent flow across the sensor. You want as close as possible to laminar, just to ensure the reading is more stable, it's not erratic based on turbulence, and it also helps extend the performance and the life of the sensor over time. You want to make sure that if you're in a bypass situation where it's a sampling type panel, you want to have enough velocity going across the sensor to minimize buildup and fouling on the sensor itself. And again, always mount the sensor perpendicular to flow. When dealing with abrasion, again, keep the sensor close to the pipe wall as possible, where the velocity is not as high as the center of the pipe, to help extend the life of the sensor. And those are kind of some of the challenges that customers will face. But those typical suggestions will help typically find longevity in your performance for the sensor. So another scenario we get asked often by our customers is, well, my sensor is responding slowly and I've cleaned it. So what's creating this issue here? So the type of cleaning solution used can make a difference as well. So general sludge, typically I recommend, for general deposits using either water or 10% hydrochloric acid, either a wash rag or a soft bristle toothbrush. And soft bristle toothbrush work really well, especially getting into the nooks and crannies, especially if the sensor has notch bars or geometry that makes it hard to get into all the nooks and crannies with just a regular washcloth. For mineral deposits, again, hydrochloric acid or hydrofluoric acid-based solutions are work really well. An example to the right is one sensor that I came across at a visit for a customer. This was about 3 years old, the sensor, but it worked really great. They said it was very stable at 7 pH and didn't really change and give them any issue. But as soon as we put it into a 4 buffer, it was basically non-responsive. So they were carrying out 1-point calibrations on 7, and for them, it passed calibration. It worked well. But as soon as you put it into anything else, it wasn't responding. And it was because of the fouling on the glass. You see the rust deposits there, but they thought it was perfectly fine. So, for this one, iron deposits, a great solution would be hydrochloric acid or HF-based solutions, which will kind of etch the rust off. And you got to keep in mind with HF acid-based solutions, you want to be careful not to leave it in too long because it will over time etch the glass itself. Greasy deposits, detergent or acetone-based solvent works really well. And then for protein deposits, for pharma type and food and bev, HCl solution with enzymes work really well as well, especially with deep penetrating plugging of the junction. Okay. Now on to our next section, which is the measurement validation portion. So this again covers what happens when my lab result doesn't match my process reading. And this happens, basically every single time you come across a sensor, because there are a number of different factors that contribute to variation between the lab result and the process reading. The one main thing is temperature. Temperature affects pH sensors because the higher or the hotter the sensor is, even if we take out changes in pH of the process or the solution out of the equation, if you have a hotter pH sensor, that output from the sensor will be much greater compared to a cooler sensor, even in the same pH solution. So the way we combat this is there's an internal reference or internal temperature element that helps compensate for this using an algorithm. And most pH sensors will have this. If you don't have a pH sensor with an internal temperature sensor, I'd highly recommend adding one. If your process is really stable and doesn't change that much, you might be okay by inputting a temperature reading. But if there are temperature fluctuations, your reading might be inaccurate. So the temperature element does compensate for that, but sometimes they are thermally lagged. So you can get a deviation from a process sensor reading to what would be like a grab sample analysis based on thermal lag potentially in the pH sensor, because it will take some time to actually adjust to the temperature of the solution. An also important factor is pH of a solution will also slightly change due to temperature. So if I could take a 4 buffer or a 7 buffer, 9 buffer, typically they'll have a label on the side that publishes readings based on temperatures. At 20 degrees C, a 4 buffer might read 4.01. But as soon as you raise it to 30 degrees C, it might show 4.1 as an example. So always keep that in mind, that solution pH will change with temperature as well. And typically most transmitters, pH transmitters, do have an algorithm not only to compensate the output of the pH with temperature fluctuations, but also the pH value as it changes with temperature. So keep that in mind. Another thing, and this is more common with drinking water, typically things that are not high the impurities in it, is CO2 or pressure. So drinking water, so you might have a sample bypass that's slightly pressurized. As soon as you take the sample out, it might vary by a few units of pH, the difference. And this can be as high as anywhere 0.5 to 0.2 pH difference from a pressurized sample to a sample that's been collected and exposed to atmospheric. So there are deviations. You're going to keep that in mind when you're comparing grab sample results to process results. The pressure can impact the value. Another impact is time, especially if there's a reaction taking place within the process that you're measuring. If I take a sample and I do an analysis an hour later, 2 hours later, that reaction could have taken place, which then affects the pH of that sample. So you got to keep in mind that you want to reduce the time frame between when you grab the sample to when you do an analysis. The shorter the possible time frame, the better off you'll be. Yeah, you also have things like sodium error. So the pH sensor does respond, obviously, to changes in pH, but things like sodium, potassium, lithium, if they're in high concentration in your process, and if you're reading very low pH levels, those can act as acid ions, or basically hydrogen ions, and mimic a more acidic solution, even though your actual pH level isn't that low. So you got to keep that in mind and calibrate that effect out if possible. And then the other is flow. So because we're dealing with salt solution in the reference electrode, depending on the flow, whether it's a static sample or a flowing sample, flow will slightly drift the response of the pH sensor because of how the KCl salt's being drawn out. So always keep that in mind. A flowing sensor or sensor in flowing conditions will most of the time not match static samples in your reading. So keep that in mind. So one way to kind of counteract the biggest challenge is temperature effects is having the temperature element located close to the glass as possible. So in our design, we actually have the temperature element, or the RTD, located right behind the glass element itself. So as soon as you start seeing a pressure change, or I'm sorry, a temperature change in your process, that element detects it quickly and it provides a more accurate result for your reading. So just keep that in mind when it comes to temperature compensation and accuracy. And then last but not least, calibration options. So customers ask often, what should I use for calibration? A 4, a 7, a 9, a 10? There are different options out there in the market. There's no right way or wrong way of doing it. I typically recommend doing the full scale. So if you're 4 and a 9 potentially. 10s are typically troublesome when it comes to either exposure to ambient conditions for too long. They start absorbing CO2 and becoming more acidic. And they're more sensitive to temperature changes. So at 20 degrees C, it might be 10, but a few degrees lower or higher, it might read 9.5 as an example. And that's compared to the 4, 7, and 9 buffer solutions, more susceptible to changes in temperature. So keep that in mind. Always use fresh solutions. Never contaminate them by putting back used buffer solutions back into the main container. Always dump it out when you're done with it, just to minimize cross-contamination. And be mindful of the fact that buffer solutions will vary with temperature. So always input the right value if you want to maintain accuracy of your readings. Now, troubleshooting is also a common scenario. We get asked that often. So, I alluded to earlier, a big one is my sensor reads fine in buffer solution, it reads fine in buffer solution, but as soon as they put it back in the process, it behaves radically. It jumps all over the place. And there could be a number of different scenarios that contribute to this, but the main one that causes this is what's known as a ground loop. And that happens when you have more than one grounding point in your sensor loop, essentially. So to understand how that works, we can kind of need to understand how a pH sensor is designed. So pH sensors originally started off as an experiment back in the 1900s, early 1900s, where a scientist put two different solutions side by side that were divided by a glass barrier. On one side, he had an acidic solution. On the other side, he had a basic or caustic solution. And he put a wire into each of the solutions and measured the millivolt between the two wires. And what he noticed is that as you change the concentration or the strength of either the acid or the base, you get a repeatable result and changes in millivolts. And essentially, that's been the same design for pH electrodes ever since. We use the same kind of technology. But because we're dealing with very small millivolt values, a high impedance or high resistance glass electrode, there can be a number of different susceptible scenarios that make this reading or the output of the sensor prone to erratic behavior or readings that we don't understand or fully comprehend. So one good way to look at it is as a circuit diagram. So if people are familiar with how circuits work, this kind of illustrates that from a standpoint of, from an electrical standpoint, how a pH sensor operates. So on the right-hand, or on the top side, we have basically the pH glass wire, and that measures the output of the pH glass. On the bottom, you have your reference electrode wire, and then you have your millivolt generator on the left side. So this is the millivolts generated from the sensor based on pH changes. Now, keep in mind, there's a resistance from the glass, and there's a resistance from the reference electrode as well that are also in series with the millivolt being generated. Now, on the right-hand side, you have your pH transmitter. Now, if you're familiar with how resistors work and the challenges of measuring millivolts, you get the greatest drop in millivolt over the greatest resistor. So if you're trying to measure the millivolts from the pH electrode, your transmitter has to be the highest resistor in that series. Now, because the glass is already in the megohm range in terms of resistance, because it's inherently not very conductive, the transmitter has to be a very high resistance reading for it to operate. And we're talking about basically over 10,000 megohms resistance. So it doesn't take a lot to ground the signal, if you look at it from that standpoint, whether from the reference wire or the glass wire. Any small leak from an electrical standpoint will cause deviation reading. So things like insulating the connectors, make sure there's no water ingress will dramatically impact the reading and short the signal essentially. So the insulation between the glass wire and the reference wire has to be at least greater than 10,000 megohms just to ensure the drop of millivolts is across the transmitter and not being leaked out to ground essentially. And because the process is grounded, you want to avoid any grounding situations, especially between the glass wire or the reference wire, because any leaks to ground from those two wires can contribute to grounding points, and that creates a deviation reading. So when you're measuring a buffer solution, that solution is actually isolated, it's not grounded. So your pH sensor might work well in that environment because you only have one ground point potentially. But as soon as you put it into the process where that is normally grounded, you'll get 2 points of grounding and your reading becomes very erratic. So that's kind of one way to diagnose how to find out if you have a grounding issue, is to check on a buffer solution. And if it is reading stable, I typically take a cable that's grounded to something. If I put it into the buffer solution and the sensor behaves erratically, I know then that there's a grounding issue. So I usually typically look at the cabling of the sensor. That's typically one point to look at. If the cable's been modified, cut, bent, damaged, nicked, cut, whatever, that usually can lead to a grounding issue. Because if you look at a pH sensor, there's usually a coax cable inside. So the inner conductor is the pH signal, and the braid on the outside is the reference signal. And it's separated by a dielectric insulator, which can vary in material depending on the application. But as soon as that material is either flattened from bending of the cable too much, cut by accident, or damaged in any way, that insulation drops down and you get a short between the pH signal and the reference wire. And that's what contributes to some ground loops potentially. Another area of ground loops sometimes is the connection. So if you're using an extension cable or you're connecting to the transmitter with the back exposed, moisture in the air or corrosive elements can get into those terminals and create a grounding situation there as well. So always ensure you check your transmitter connections, make sure they're clear of rust. If there are any rust, obviously replace the terminals if you can, and always ensure your connections between your sensor and extension cable are always protected from moisture. And again, this is more of an issue with analog type sensors. Digital sensors, which have their own benefits, are more robust in that regard. They typically are not as susceptible to moisturing or susceptible to degradation of signal because it's a digital communication between the sensor and transmitter, so it's not susceptible to those environments. So that brings us to the summary section. So hopefully we brought some understanding of how to alleviate some of the issues when it comes to sensor selection. Make sure you have the right product for the right application, depending on the design of the glass, the reference proposal as well. We also covered some maintenance aspects of how to clean the sensor properly, use the right solutions, how to match lab results or benchtop results to the handheld or the process reading, and then also covering some ground loop issues that you might commonly find in your process. If you do want additional information, ABB does offer a pH care package for our customers. Basically, it's a pH school, so we do come on site and provide some more extensive and more formal training on pH theory, applications, how to do maintenance properly on your process. We also provide an assessment of your process, a life cycle assessment. So we go through the process itself, run down, make sure the installations are done correctly in the right ideal location. We also go through the operating procedures of what you currently do, how we can improve that as well, depending on if it's maintenance techniques or solutions. And then we also provide remote monitoring assistance for if you have questionable results and data that you want to go through, just to have a third set of eyes on it to look through, and also guarantee performance and longevity in your process. So that is available, and links to that information will be provided to you at the end of the slide. So at this point, we'll spend about 15 minutes going through Q&A. If you have any questions, again, if you go through the chat feature at the very top, you should be able to select your questions, and we'll go through them at this point to go through. So thank you, everyone, for your attendance.
Thanks, Nick. Thanks for the presentation. And if I could just ask Jimmy and Gus, if you can put your camera and mic on, that would be great. And maybe we'll give Nick a bit of a break since he's been presenting. So maybe first question, I know we did get some questions come in on the chat as well as the Q&A, which is fine. So I'll address the first one. A question on the chat asked, will there be a certificate of attendance for this webinar? Yes, we can definitely do that. So we'll send out everybody a certificate showing that you attended this webinar, and we'll send that out to everybody on the webinar right now. So thank you for that. And maybe a question that you can answer, Jimmy. Let me have a look down the list here. Maybe this one. How often should you calibrate a pH probe? So maybe if you could address that question. That was from Bob.
Thanks, Rob. So what I typically recommend is to calibrate a buffer calibration monthly using the buffers that Nick talked about earlier. Additionally, it might be good to do a weekly grab sample check, but I wouldn't ever make any changes with the grab sample unless it's 0.5 or greater. And if you're constantly having to make changes, then needing to look at some of the things Nick talked about with cleanings and stuff like that.
Thanks, Jimmy. We've got a few more questions coming in on the chat as well. So let me just address the Q&A ones that came in first. This came in really early on, Nick, this question, but Henry asked, what about high purity applications? Now, I know you did talk about those during the presentation. I'm not sure exactly what context that was in, but maybe if you just want to address high purity applications real quick, that'd be great.
When it comes to glass selection, you have a bit more flexibility, but typically we recommend something with a low resistance glass. So low temperature typically offers low resistance, and it makes it more responsive in those environments, or less challenging in those environments. But more importantly, it's the reference design. We want a reference electrode that is packed full of KCl salt if it is a sealed design, because I mentioned sealed designs aren't really ideal for high purity. There are versions that have like a slurry of KCl salt, which makes it less maintenance prone. But it won't last as long compared to a refillable design with KCl salt being added to it. So when you're looking at high purity, keep that in mind. You want something that it could be preferably a refillable design that keeps the operation sensor working longer and longer. Because at the end of the day, what's going to kill the sensor in high purities is not so much the glass dying, it's going to be the reference electrode dying quickly. So you want to make sure that you have the ability of topping off KCl salt within that electrode. That's going to be the most important. Right. And then iron buildup, things like that. So typically, if it's steam generation, iron is going to be a big problem. So HF-based cleaners or hydrochloric acid cleaners to etch that glass, because again, you might not see the iron buildup on the glass, but it is impacting responsiveness. So having HF works the best, in my opinion. But again, keep it very quick, a low concentration, just to etch the glass and remove the iron, and then basically clean it and put it back in the process.
Great, thanks, Nick. Yeah, next question came in from Brad. Maybe Gus, if you can take this one. The question was, when a pH sensor drifts, does it tend to drift high or low? And does it consistently drift the same way?
Yeah, that's a good question. And the answer, I guess, is it's very dependent on the application and the sensor. So it depends on if the drift is related to a reference issue, whether that be an impedance change on the reference wire, like Nick talked about, the poisoning side of it, or if the drift is caused due to a depletion of KCl, or if the depletion is caused due to an issue with the glass electrode, the measuring side of the probe. And so you'll see drift kind of go either direction. What's important to look at is how much it's drifting. So if you should see maybe during your weekly grab samples or your bi-monthly calibrations or whatever frequency of calibrations you're doing, and the drift is occurring more and more, or you have to process calibrate more frequently, that's an indication that it may be time to try to clean the probe or to replace the probe.
Great, thanks, Gus. Another question here from Fang Yi. What is the general use life for the probe for a mild condition if the glass is aging? So I didn't quite pronounce that correctly, but what's the average general use for a probe in a general application, I guess, with a glass probe? Nick, if you want to try and address that one, probably didn't word that well. Sorry, but
my mentor always said famously, anywhere from 5 minutes to 5 years. So pH glass will vary in terms of lifespan, and it depends on the application. There's no clear way of indicating how long it will last, but there are methods of extending life. So maintenance aspects can help extend it. How you mount it, again, mounting locations play a huge impact in how long a sensor works. So making sure, again, the laminar flow across the sensor as much as possible helps extend, limiting the fouling effects. I think someone mentioned, Victor mentioned about, he mentioned bulb style glass is actually better for fouling, or it was told bulbous type glass is better for fouling. What I've seen in my experience is that the bulbous glass actually can generate eddies. So if you get abrasion, they actually hit the back of the glass, whereas the flat glass has basically a minimal profile. So the process typically just slides past it. So it minimizes the abrasion and fouling effect. So those can all kind of contribute to the life of the sensor and help extend the life of it.
Great, thanks, Nick. I'm going to jump down some other, because we got a lot of questions coming, so I really appreciate everybody sending the questions in, and we're going to try and get through as many of these as we can. And if we don't have time to do this, we'll definitely come back to you with the answers as well. So there was a question here from Samuel saying, my hand probe says to calibrate every single day. Is this really necessary? We generally don't need pH values more than accuracy, plus or minus 1%. So I don't know if Jimmy, if you want to take that one, or Nick or Gus.
Well, just like I mentioned earlier, I'm not sure why it says to calibrate every single day. That might be a little much, unless you guys are doing some type of like environmental outfall sampling where it requires you to do a sampling or a testing or buffer calibration every single day. But like I talked about before, I think monthly buffer calibration would probably be adequate. If you're doing a hand probe type thing, you could potentially do that one weekly. But for normal process calibrations, monthly calibrations with a grab sample check weekly, you could even put this inside of a buffer, like a 4 buffer or 7 buffer, and verify that that is accurate before you use it. And that might be more feasible for what you're doing.
Thanks, Jimmy. Maybe one for you, Gus. This is from Braden, can you measure in-process pH of organic solutions with an appropriate sampling system?
So I guess the question would be what type of organics. If we're talking about like in wastewater applications, sure. We have a line, our 500 series, the 500 Pro, which is specifically designed for those kind of harsher applications in wastewater, as an example. We've also have our TB5 line, which is our older generation, which Nick alluded to, that has the wooden core that will try to slow down the poisoning effects of all those, maybe it's the organics or just the harsh chemicals that you might be experiencing, getting up inside the probe and causing interferences with the reading. So, I hate to say it depends on the application, but as you've probably seen over the last 30 or 45 minutes, pH is very dependent on the application. And that's where Jimmy, Nick, and I can come in, look at your process conditions, look at your application, and try to come up with the best solution. for your application.
Yeah, thanks, Gus. As I said, we got some questions coming in the chat. Some of these are visible, I think, to everybody, some aren't, but some of them are very, very long. So I'm not sure we're going to get to those on this particular call, but we'll definitely come back to you with an answer on some of these, but maybe go into one of them that's a little bit shorter. Question is, in terms of cleaning of pH probes on a clean water application, what concentration of citric acid would you recommend? So maybe Nick, if you want to take that one.
Yeah, citric acid, typically, I mean, you don't want anything too strong. Acids are typically more, I don't want to say gentle, but they're easier on pH glass than something like a strong caustic. Because most applications, if you're running acidic, you typically want to use a caustic to clean. And if you're running caustic, you typically use an acid. So acids typically are more gentle. They don't damage the glass as easily as a strong caustic would. But you typically don't want to go over 5–10% for citric acid when it comes to cleaning. You want to kind of leave it generally mild. So yeah, citric acid, hydrochloric acid is a common one, typically for cleaning. Sulfuric acid, I typically would stay away from, only because what happens is it bombards the glass with hydrogen ions. It becomes dust responsive. It actually just super saturates the glass, and it becomes just stuck on low pH and doesn't really respond. So I would typically avoid sulfuric acid.
Thanks, Nick. Another question here from William. If your process is always under 4.6 pH, should you calibrate at a 10 pH point?
Good question. I mean, typically, I try to do the full scale just so that you set the response to this at an appropriate level. If you start diving into, and this is fine too for applications where they're typically just on the low end, that's fine. But if you have a dynamic process which varies greatly, you typically want to have the maximum ends, so a 4 and a 9. I typically don't recommend a 10 unless it's absolutely necessary, only because the temperature effects are that much greater on a 10 buffer. But if you're running on the low end, you can typically do a 4 and a 7 to match that span. But keeping in mind, if it does vary greater, you might not be tracking that results. Even though it's linear, I always typically recommend maximizing the ends for your buffer calibration.
Great, thanks, Nick. Question here from Ben. Maybe back to you, Jimmy, on this one. Do you have any experience measuring pH measurements below 0? I have a sulfuric acid solution. I would like to measure online pH, but found it difficult to find something that would work for me.
Mm-hmm.
That might be a good question for Nick, because I have not had experience measuring less than 0.
Yeah.
I'm sorry. Okay, go ahead, Nick.
Unfortunately, sulfuric acid, especially at a very high concentration, as I mentioned, becomes, and tell me if I'm wrong, but it becomes very non-responsive. It kind of gets stuck at that low pH range. And as I mentioned, it's the bombardment. So there's not really much of a solution to use in those environments. There are other technologies in glassware, but again, they're not designed for extreme ends of the pH scale. So glass is probably your main option for those environments. If there's a way you can measure it, maybe on a diluted, or it's not really possible usually, but there's not really much options, unfortunately, for really low end pH. It'll just become very non-responsive at the very low end. So picking the right glass would be the only really option. Selecting that glass type would help. So yeah, HF glass would probably be the one I would recommend, or HF type glass.
Great, thanks, Nick. Actually, I saved all the easy questions for me, so I'm going to answer the next one. So Paul asked, can I get a copy, or are we going to get a copy of today's slides? So the answer to that is yes, we are going to send you a copy of all these slides. So just so everybody knows when we send that out. So question here from Joe. What is considered safe or normal velocities to avoid damage, but protect against fouling or inaccurate readings? I don't know who wants to jump in on that one. Gus?
Yes.
Go ahead.
Yeah, sure. I can do that. So if we talk about hot tap or insertable pH probes versus flow cells, it's a little bit different than high purity is a little bit different. But if we just talk generally, as Nick alluded to, you want laminar flow. So air is not conductive. And so when you put your sensor into like a hot tap situation, you do not want to insert the probe into the top of the pipe. You want to make sure that it's in solution at all times. Additionally, if you have a vertical riser, you want to make sure that flow is going up, not going down. So you want to make sure that it's as laminar flow as possible. The velocity is not as important necessarily unless we're talking about the process is just really getting after it. Then you'd have to be concerned about mechanical damage to the hot tap. Now, when we talk about high purity applications, like in a flow cell, it's very important that we control flow and velocity. And so in those applications, we typically put things into a flow cell and control flow with a rotometer down to 5 to 6 feet per second, and a 1/4 inch that would be about 150 to 200 cc's a minute.
Thanks, Greg.
So, yeah, so it depends on how you install the probe.
Okay, so we've got some long ones in here. Let me go. There's one from Steve. So bear with me on this question. So let me just read this. This is going to be one for you, Nick, right? So
Yeah, I can summarize quickly.
Okay, go ahead. Yeah, you've seen how you've read it. So go ahead. Yeah.
So Stephen mentioned, he has 2 points of contact in the process. They match on the lab reading. When they're out of the process, they read correctly. But as soon as you put it in the process, there's a deviation. And typically they do a 3-point cal. So that's the tricky part. As I kind of alluded to earlier, the process reading will never, most times will not match the lab results and the handheld results for the issues that we raised earlier, such as flow conditions, things like that, and temperature deviation. So what I recommend typically to align the readings is you do a 2-point calibration in buffer solutions outside the process after you do cleaning. You put the sensor back in, you let it stabilize for a couple minutes. Once it stabilizes, then you do a 1-point adjustment to then match the handheld result or the lab reading that you have, and to line up all the measurement points together. That's typically what happens, because there are conditions in the flow or in the process that will deviate the measurement slightly. And that's one way of kind of bringing it together and make sure that you line up when you do the validations.
Thanks, Nick. There's a question also in chat. I'll read out. Where does pH differ for static and dynamic, and in parentheses, under mixing or stirring for the same solution? What is the preferred way for measuring pH with or without stirring? Question mark. So maybe I don't want to take that one. If you want to take that one, Jimmy or Greg or sorry, Gus or Nick.
Yeah, I can take it.
Okay,
so and this goes for buffer calibrations. This goes for process verifications, like taking a grab sample. We've done in a previous life some experiments on this, and the pH does differ based on whether you have it in a static environment to where there's no mixing, or if you have a magnetic stir bar. And what is most important, or at least what we found is most important, is consistency. That you measure your pH the same way every time. Everyone measures it the same way every time. Whether you're doing a buffer calibration, you're doing a process verification, you're taking a grab sample, it's that everyone does it the same way. So I would implore you to talk to your lab staff, talk to your operators, and make sure that everyone is consistent in their grab sampling methods and in their buffer calibrations.
Great.
Yeah, Gus, just to piggyback on the last piece of that you said, a good standard operating procedure would keep that going, right?
Excellent. Thank you. So maybe we'll take just one more. We're reaching the top of the hour here, and I really appreciate everybody joining us today and appreciate all the presenters. Thanks for joining. Just one more question we'll do here. And as I said, we couldn't get through everything. We really do appreciate all the questions that were asked. We will get back to everybody with all the answers to these questions, so you'll see them. But maybe just one more. How can one tell the need for sensor replacement in a cyanide destruction application due to the cyanide being in the waste or in the waste? Maybe Nick, if you want to finish with that one.
Yeah, so typically a gauge or a benchmark for when a sensor needs replaced is by performing a 2-point calibration. That really tells you the health of the sensor. A 1-point adjustment typically won't tell you much. You need a 2-point calibration. So the results of a calibration will typically give you a percentage or a slope reading or efficiency value. It could be presented as a percentage point or millivolts per pH. And then there's an offset value, typically a millivolt value or pH value offset. So typically, ideally at 100% slope, that's a brand new sensor that's perfect working condition, or 59 millivolts per pH, that's perfect condition. But as soon as you start dropping down, typically to around 80, 60% in that ballpark, what happens is the responsiveness of the sensor becomes more sluggish. It doesn't see the full potential that it should. So as an example, at 7 pH, or that's a bad example, at 9 pH, typically you would see a negative 120 millivolt value. But over time, it might not see that full potential. It might start seeing negative 100, negative 90, negative 80, and it'll become lower and lower and lower with time. And that's because the glass is becoming less sensitive or not as responsive. So you'll start seeing a degradation response that way. So typically, it depends on the application. Some customers are okay running down to 60% efficiency. Some will cut it off at 80%. But the lower the slope reading or efficiency, the slower responding the sensor will be, the more deviation you'll see. And then there's an offset value that also comes with the calibration. So typically anything above 2.5 pH or 180 millivolts, 280 millivolt range, that typically indicates a poisoning effect or a migration to that KCl or that process towards the reference electrode that we talked about earlier. The higher the millivolt value, typically the closer that process is to the reference electrode and the sooner it is to the end of its life. So I typically recommend using the slope and the offset as benchmarks of when it needs to be replaced and with those values.
Great, thanks, Nick. Well, with that, we'll close up. Thank you so much. We really appreciate you attending and joining us today. And thanks to Nick, Jimmy, and Gus for presenting. And hopefully we'll talk to you again soon. Thank you very much.
Thank you.